Stand at the North Pole, holding a spear out horizontally, pointing along the ground, down the line of longitude that runs through London. Walk south along that line to the equator, keeping the spear pointing dead ahead, and never once twisting your wrist. At the equator, turn your body a quarter turn and walk east for a quarter of the way round the world, still not twisting the spear so it now points sideways across your path, out over the water. Turn again and walk back up to the pole. You arrive exactly where you set off, and the spear is pointing a quarter turn away from where it pointed when you left. You never turned it, nobody turned it, it came home rotated.
There is an exact number in that, not an approximate one. The angle the spear turns through equals the area of the patch of ground your walk fenced off, divided by the square of the Earth's radius. You fenced off 1/8 of the sphere. The whole sphere in those units is 4 pi, an eighth of that is a half of pi, and a half of pi in radians is a right angle. Exactly, with no correction terms.
What happens if I dawdle? Suppose I sprint the first leg, stop for a fortnight on the equator, and crawl the third on my hands and knees. Does the answer know any of that?
The same right angle. Take a week or take a year, sprint the first side and drag the third, and the spear comes home turned by exactly the same amount. Nothing in the answer knows how fast you went, or when. It knows only which patch of sphere your path enclosed. That is the word geometry doing its work. The result depends on the shape of the trip and on nothing else whatever about it.
But what did the turning? At every step, I am holding the thing as straight as a human can hold anything. There is no moment where I cheat, no force acting on it, no talk anybody could write down. Film the walk. Stop the film on any frame you like, and you see a spear being carried without being turned. And the first frame and the last frame disagree.
No moment, no cheat, no force, and no cause you can put your finger on. Every individual step is honest, and the sum of honest steps is a rotation. That is the entire difficulty of this hour, and also its entire content. And you have just met it in a version you can watch, which is why we started on foot, rather than in a Hamiltonian.
Say the transplant before we make it, because I would like to know what I am aiming at. What is the quantum sentence that corresponds to the spear, and what plays the part of the direction the spear points in?
A quantum state, dragged slowly round a closed loop of conditions and brought back to the conditions it started in, comes home rotated. In a sense I have to make precise, by an amount fixed by the shape of the loop, and not at all by the speed. And I will say plainly what kind of hour this is. It is the most abstract in the course. Nothing goes milky, nothing climbs a wall, nothing levitates. There is one object to hold on to, a single spin, a magnetic field, a hand that moves the field slowly.
You left me with exactly that image at the end of the last conversation, and the reason you gave was that we have run out of things that get chosen. Nothing broken, nothing selected, no quantity growing out of zero. And two states of matter that are nevertheless not the same state.
We have. Everything for 4 conversations has rested on a quantity that is 0 on one side of a transition and not 0 on the other. What is coming is a pair of states of matter with no choice, no broken symmetry, and no order parameter. Demonstrably different states, told apart to a precision that makes everything we have done look approximate. The difference is not in what the wave function is anywhere. It is in how the wave functions at neighboring conditions fit together. Today builds the tool and does not yet use it.
Set the system up properly then, and slowly. Because if this is the abstract hour, I want the scaffolding nailed down before anything gets built on it. What is the system? What is the knob I am turning? And what am I allowed to assume about the way I turn it?
One spin. An electron's, a neutron's, a proton in a water molecule. It does not matter which. Put it in a magnetic field. Its energy depends on whether it points along the field or against it, and the two energies are split by an amount proportional to the field strength. Two states, a gap between them, and the gap is yours to set, because you are the one making the field.
And the knob is the field.
The knob is the field, and here is the move that matters. Not its strength, its direction. Fix the magnitude, 1 Tesla say, and hold it there for the whole experiment. Change only where the field points. Now the direction of a field is an arrow of unit length, which is a point on a sphere. So the space of settings available to me is the surface of a sphere, and moving my hand traces a path across that surface.
I want that named carefully because it is a parameter space, and not a space anything sits in. Nothing is located at those points. They are dial settings on the apparatus. If I draw a path across that sphere, I am not drawing a trajectory of the spin. I am drawing a history of my own hand.
Nothing is located at those points, and I am glad you said it now, because that distinction gets slippery later, and I want it clean beforehand. The sphere is a catalogue of magnets I could build. The spin lives in a laboratory. The loop lives in the catalogue.
So I move the hand. Slowly, I assume.
Slowly, and slowly is a criterion here, not a mood. Born and Fock proved the relevant statement in 1928, and Cato made it rigorous in 1950. If a system starts in one of the instantaneous eigenstates, and you change the Hamiltonian slowly, compared with the gap divided by Planck's constant, the system stays in that instantaneous eigenstate. It does not get kicked across. The spin keeps pointing along the field and follows it round.
I need a number for it because slowly compared with the gap over h bar is still just a phrase until I know whether it is a laboratory tightrope or something anybody satisfies by accident.
In a field of 1 Tesla, the splitting of an electron's spin corresponds to a frequency of about 28 gigahertz. So, slow means moving the field round in a time long compared with a few tens of picoseconds. Turn it round in a millisecond and you are slow by a factor of 10 to the 7. It is a formality. It is hard to be fast enough to violate it on purpose.
So the spin follows the field round, and at the end of the loop it is pointing exactly where it pointed at the start, in exactly the field it started in, having taken however long it took. Which sounds like a precise description of nothing happening.
The direction came home. The direction is not the state. Everything today lives in the space between those two sentences, and to open that space, I have to talk about the one thing in quantum mechanics you are taught, correctly, that you cannot measure.
The phase.
The phase. A quantum state is not a probability distribution, it is a complex amplitude, and a stationary state carries an internal rotation. The amplitude turns in the complex plane at a rate given by its energy divided by h bar. Picture a clock hand glued to the state, going round. High energy, fast hand. Low energy, slow hand.
A clock hand nobody can read though, because the overall phase of a state is not observable. That is on the first page of every book I have opened, and it is always offered as a reassurance. Do not worry about the phase, it cancels. You are about to tell me it does not cancel.
On the first page of every book, and every book is right. Multiply a state by a phase, and every expectation value is unchanged. On its own, the hand is invisible. It becomes visible in exactly one way. Comparison. Take two copies, do something different to each, bring them back together, and let them interfere. What you see is the mismatch between the two hands, and the mismatch is a counted, measured thing. Fringes move across a detector.
So the experiment I should be picturing is an interferometer, with the spin taking the scenic route on one arm and sitting still on the other. What comes out at the end is not a phase, it is a fringe position, the disagreement between two clocks that were synchronized when they parted.
That is exactly the experiment, and versions of it have been done. I will name them later. Two copies of the spin. On one arm, the field never moves. On the other, it is walked slowly round a closed loop of directions and set back precisely where it began. Identical strength throughout, identical energy, identical duration, identical field at start and finish. Recombine the arms and ask whether the fringes have shifted.
The expectation is that they have not. Each hand turns at its energy over h bar. The energies are equal because the field strength never changed on either arm, and the elapsed times are equal because they ran together. So both hands turned by the same amount, and the fringes are exactly where they were.
Work it through out loud and tell me what you get.
The magnitude of the field is fixed, so the energy is fixed at every instant on both arms. So the accumulated turn on each is the energy multiplied by the total elapsed time, divided by h bar, and the total elapsed time is the same on both. The difference between them is 0. And if you tell me there is something left over on top of that, then it must be a failure of the adiabatic approximation. The approximation is not exact, it leaks, and the leak gets smaller the more slowly you go. So run the loop twice as slowly and the leftover halves. Run it slowly enough and it is gone.
The first half of that is right, and the second half is the mistake this whole subject is built out of. There is something left over. It does not halve. Go round twice as slowly, and the clock part, energy times elapsed time, doubles, exactly as you said it would. The leftover is unchanged. 100 times slower, unchanged. It is not an adiabatic correction. It survives the slow limit, which is the limit that was supposed to make everything trivial.
Where can it possibly come from? I subtracted the energy, and I was under the impression that the energy is the only thing in quantum mechanics that generates phase. That is what the Schrödinger equation says. Nothing else in the problem has a rate attached to it.
You subtracted everything with a clock in it. Here is what you did not subtract. At each field direction, the state, spin pointing along the field, is a particular vector. And to write it down at all, I have to make a choice. I have to decide which complex number counts as its phase at that direction. Now take one step along the loop to the neighboring direction. The state there is a different vector. Ask whether it lines up with the one before, or whether it is turned slightly relative to it.
Turned relative to it? In what sense? Those are eigenstates of two different Hamiltonians, at two different field directions, and I have always been taught that comparing the phases of states belonging to different Hamiltonians is a meaningless thing to do. What licenses the comparison?
The fact that they are vectors in the same space. Two different Hamiltonians, yes, but both of one spin, and a spin has a two-dimensional state space, whatever field it sits in. So overlap the two states. The overlap is a complex number, and its phase tells you exactly how much the second fails to line up with the first. That mismatch is a property of two neighboring field directions and of nothing else. There is no time in it. It cannot know how long you took to move between them.
Add those up all the way round.
Add them all the way round the loop, and you have the leftover.
Say it again with the emphasis in the right place, because I think that one contrast is the whole hour, and I want it in a form I could repeat to somebody who was not here.
The dynamical phase is a sum over when. The leftover is a sum over where. Time appears in the first and is absent from the second. Not negligibly absent, structurally absent, because every term in the second sum is fixed by two neighboring settings of the apparatus and by nothing else at all. Slow the trip down and you multiply the first sum and leave the second exactly where it was. Michael Berry published that in 1984 in the Proceedings of the Royal Society in a paper called Quantal Phase Factors Accompanying Adiabatic Changes.
1984 is 56 years after Born and Fock. The adiabatic theorem is in every graduate course. The calculation is a couple of lines of a kind anybody could do on a train, and nobody looked in the remainder for half a century.
People looked at it and discarded it for a specific and respectable reason. It is a quantity you are entitled to delete.
Delete? On what grounds?
On the grounds that I made a choice. I said I had to decide the phase of the state at each field direction, and that decision is mine and arbitrary. No physics fixes it. Suppose at one particular direction I multiply my chosen state by some phase of my own invention. Every overlap that involves that direction changes. So the mismatch at a single step is not a physical quantity. It is an artifact of my labeling, and by relabeling, I can make any one step's mismatch come out however I like.
If every term in the sum is arbitrary, then the sum is arbitrary, and there is nothing there to measure. That is not even a subtle argument. That is one line, and it disposes of the whole quantity.
For a path with two loose ends, that is exactly right. And it is why the quantity sat in the bin for 50 years. Close the path and it fails. Follow my relabeling round the loop. Every direction appears twice in the sum, as the far end of one step and the near end of the next. My invented phase enters those two terms with opposite signs and cancels itself. Everywhere, including at the start, because the loop closes and the starting direction is also the finishing one. The total round a closed loop does not depend on my choices anywhere.
The individual term is meaningless and the closed sum is real. I can follow the cancellation, but I do not yet believe it in my hands. Is there an everyday version?
What time it is in London? Somebody picked Greenwich. The choice was free, and every other town's clock setting was equally free. Sail west round the world, resetting your watch at every border by whatever local convention holds, and each individual reset is a convention. Come home, and you have counted one sunrise fewer than the people who stayed. That discrepancy is not a convention. Every local choice was arbitrary. The loop total was not.
The sunrise is a real event, and Greenwich is a committee decision. That I can hold. And there is presumably a name for the structure, because mathematicians will have got here first.
There is, and Barry Simon supplied it. His paper appeared in Physical Review Letters in December of 1983, a few months ahead of Berry's own. The rule for comparing states at neighboring parameter values is a connection, in the sense differential geometry uses that word, and the rotation you find on returning is its holonomy, the same object that turns the sphere. He also noted that integers Thouless and colleagues had just found in a quite different problem could be read the same way. That remark is where the next hour begins.
I do not have names for any of these pieces, and I will invent private ones if you do not stop me.
The leftover is the geometric phase, or Berry's phase. The local rule underneath it is the Berry connection, which is not observable. And the density I am about to define, the amount of phase per unit area of parameter space, is the Berry curvature, which is.
What is the leftover then for my spin? When I walk the field round a loop of directions, what number comes out?
Guess it before I tell you, because you have enough to guess with. What could it depend on? Not the field strength. That only sets the energy, and we subtracted the energy. Not the speed. Not the particle's mass or magnetic moment, because those live in the energy too. What inputs are left?
Only the loop itself. Only the curve, the field direction traced on the sphere. And the only property a closed curve on a sphere has that does not depend on where I chose to put my axes or how I chose to orient the sphere is how much area it encloses.
How much area it encloses, measured as a solid angle seen from the center. So the answer is forced to be a pure number times the enclosed solid angle, and the only content left is that pure number. For a spin 1/2, it is a half. The geometric phase is half the solid angle enclosed by the path of the field direction.
And for the sphere on the Earth, it was the whole solid angle, with no half in front of it. So the half is not a feature of the geometry, it is a feature of the thing being carried round the geometry.
With no half because the sphere is a vector, which behaves like spin 1, and the general answer carries the spin as a factor. I am skipping the calculation that produces the half. What it does is overlap two spin states whose axes differ by a small angle, and the half is the half angle that shows up whenever you rotate a spinner rather than an arrow. The same half that makes a spin need 2 full turns to come back to itself.
How large can this get? Take the field direction round the equator.
Walk the field direction once round the equator of the sphere of directions. The equator encloses a hemisphere which is a solid angle of 2 pi. Half of that is pi. A phase of pi is a multiplication by -1. The spin comes home as exactly minus itself.
Which, if I only ever measure which way it is pointing, is nothing at all. But in the interferometer, it is the largest effect available. A phase of pi turns constructive interference into destructive. Every bright fringe becomes dark.
Every bright fringe becomes dark, and nothing else about the run changed. Same field strength at the start and the finish, same energy the whole way, same duration on both arms, spin pointing the same way it was pointing at the beginning. Every quantity you would have written in the notebook is unchanged, and the pattern is inverted.
I do not believe a middle without its limits. What happens to a small circle up near the pole of the sphere? A loop I could walk the field round in a second.
Small enclosed solid angle, small phase, going smoothly to 0 as the loop closes down to a point. Walk the same loop the other way round, and the enclosed solid angle changes sign, so the phase changes sign. Walk it twice, and you get twice the phase. All of which is what you would demand of anything built by adding up contributions step by step along a path.
There is an ambiguity in what you just said that I cannot get rid of, and I want to know whether it is fatal. A closed curve on a sphere fences off 2 regions, not 1. There is the cap, and there is everything else. Which of the 2 areas am I supposed to use?
Either one. And that is not a shrug, it is the most consequential sentence of the hour. The 2 regions add up to the whole sphere, 4 pi, so the 2 answers differ by half of 4 pi, which is 2 pi. A phase of 2 pi is 1 complete turn of the clock hand. No difference at all, the state is identical. The ambiguity is exactly invisible. Not nearly. Exactly.
So a question I have no way of answering turns out to be a question with no consequences, which is a suspicious sort of luck, and I do not think it is luck.
And it could not have come out otherwise. The phase is measurable, and the choice of which side of a loop to call the inside is not a physical fact. Had the 2 answers differed by anything but a whole multiple of 2 pi, the theory would contradict itself. That argument, an ambiguity obliged to come out invisible, forcing a quantity to be an exact multiple of 2 pi, is the one thing from today you will meet again, and next time it comes back as an integer somebody reads off an instrument.
You have handed me a phase that belongs to a whole loop, and loops are awkward objects to think with. Is there something underneath it that lives at a single point in parameter space, the way a field does?
There is, and it is the second half of what we are building. Take a tiny loop around one field direction, enclosing a small patch of the sphere. Its phase is proportional to the patch's area. Divide phase by area, shrink the patch to nothing, and you have a density. Geometric phase per unit area, defined at every point of parameter space. That is the Berry curvature, and the Berry phase of any loop is the total curvature it encloses.
A density whose integral over a region is the phase of that region's boundary. That is precisely the relationship between a magnetic field and the flux through a circuit.
Precisely that relationship, and we are going to lean on it hard in a few minutes. First, What does the curvature actually look like for our spin? Go back to the sphere and notice that the sphere was a slice. I fixed the field magnitude at 1 Tesla. The genuine parameter space is all magnetic fields, every strength and every direction, which is a three-dimensional space, and my sphere is a shell inside it, at radius 1 Tesla.
And at the center of that shell, the field is 0, which is a setting I could dial up perfectly easily by turning the magnet off.
At the center, the field is 0, and at 0 field, the two spin states are degenerate. No along and no against. The energies coincide. The gap the adiabatic theorem requires has closed. At that one point in the whole of parameter space, everything we have said stops working. And the result? The Berry curvature in that three-dimensional space is exactly the field of a point source at that center, radially outward, falling off as the inverse square of the distance, total outward flux fixed. A magnetic monopole in parameter space, of charge 1/2.
Which is where the half came from. The flux of a monopole through a cone is its charge multiplied by the solid angle of the cone, and my loop on the shell subtends exactly such a cone.
That is where the half came from. Now notice what the geometry is made of. Take the degeneracy out of the family altogether, hold the two levels apart at every setting, including settings you would have to build a different apparatus to reach, and the curvature goes with it. Leave it in, and the curvature is fiercest where the gap is narrowest, and dies away as you move off from the touching point. The curvature is the shadow cast by a place where two levels touch. The most portable sentence available today. A geometric phase is what a nearby degeneracy does to states that never go near it.
And mine never does. My loop sits at 1 Tesla the whole way round. I am always the same distance from that point. I never approach it, and I never encircle it in the ordinary sense. And it determines the answer completely.
It determines the answer completely, at arm's length, from a place the system never visits. If that reminds you of something, keep hold of it. I will ask you for it shortly. One piece of history first. In the same volume of the same journal as Berry's paper, immediately in front of it, Berry and Michael Wilkinson published a study of these degeneracy points. Where two energy surfaces touch in a two-parameter family, they meet as a pair of cones joined tip to tip. They named them diabolical points after the diabolo, the double-coned toy on a string.
A name that tells you the shape and also tells you what they cost the people who ran into them. And the useful half is the shape.
Every diabolical point in a parameter space is a source of curvature, and every geometric phase anybody has ever measured can be traced back to 1.
You told me to hold a thought. I have it. And I want to know whether I am hearing a real identity or a rhyme, because it would be easy to fool myself here.
Say yours first.
Aharonov and Bohm, 1959. A long solenoid with its magnetic field entirely confined inside it. Split an electron beam and send the two halves past on either side, through a region where the field is exactly 0, so classically nothing acts on them, because the force law only knows about the field where the particle actually is. And the interference pattern shifts anyway, by an amount set by the flux enclosed between the two paths. Flux the electron never entered.
By the enclosed flux, in units of Planck's constant over the electron charge. And it is an identity, not a rhyme. In both cases, there is a rule for comparing phase at neighboring points. That rule is not itself observable, and the observable is what you get by going round a closed circuit and enclosing something. Aharonov and Bohm circuit is in ordinary space and encloses real magnetic flux. Ours is in the space of magnets I could have built and encloses Berry curvature. Structurally, it is one object.
Where does it stop? Because that analogy is doing an enormous amount of work, and I want to know what it is not allowed to do.
It stops at the word real. The solenoid's field is a magnetic field. quote it in Tesla, account for the energy stored in it. Berry curvature is not a field in space and is not in the laboratory at all. Nothing sits at the point where our monopole is. The monopole is a statement about how the eigenvectors of a family of Hamiltonians fit together as you move through the family. You cannot put a compass next to it, you cannot store a jewel in it, and nobody has ever found the real article anywhere. Take the mathematics across and leave the ontology behind.
Was the Aharonov-Bohm shift measured, or is it one of those effects everyone believes and nobody has seen?
Measured within a year. Chambers in Bristol, 1960, used a whisker of iron about a micron across as his solenoid and an electron microscope as his interferometer, and watched the fringes shift. The objection, pressed for a quarter of a century afterwards, was leakage. No magnet confines perfectly, and stray field outside would give the shift by ordinary means. Tonomura and colleagues shut that down in 1986 by trapping the flux inside a tiny donut-shaped magnet coated in a superconductor, which by the Meissner effect expels the field entirely. The shift stayed. There was nothing outside.
The Meissner effect, used as a piece of laboratory hardware rather than as a phenomenon to be admired. 2 conversations ago, it was the thing being explained. Here, it is the guarantee that makes somebody else's measurement mean anything.
As the only available guarantee that a region of space genuinely has no field in it. And the answer that came back is the one the theory demands. The electron responds to the flux it encircles and not to any field at its own location.
You have been saying Berry's phase for half an hour. Was it his?
His in the way that counts. He saw it was one thing rather than a curiosity of a particular problem, and wrote the general statement with no system in it. But it had been found before, more than once, and each time mistaken for a fact about the system it turned up in. The earliest and the most startling is Pancharatnam.
I have never heard that name, and I suspect that is the point of the story. Who was he? When? And what was he working on?
Shiva Ramakrishnan Pancharatnam, 1956, in the Proceedings of the Indian Academy of Sciences, in a paper called Generalized Theory of Interference and Its Applications, communicated by his uncle C.V. Raman. He was 22. The subject is polarized light. Every state of polarization, linear at any angle, circular either way, elliptical in between, is a point on a sphere, the Poincaré sphere. Send a beam round a closed cycle of polarization states and interfere it with a beam that stayed put. The phase difference is half the solid angle of the closed path.
Half the solid angle, that is our sentence, word for word, 28 years earlier, in classical optics, with no quantum mechanics anywhere in the room.
Word for word, and with no quantum mechanics, which tells you something important about what we have been doing. This is not a quantum effect. It is a fact about how you compare a 2-component complex amplitude at one setting with the same object at a neighboring setting, and the polarization of a light beam is exactly such an object.
What became of the paper? Because a result that general, sitting in a journal for 28 years, ought to have been noticed by somebody.
It was read by people who worked on polarization optics, and by almost nobody else. He went to Oxford in the mid-60s and died there in 1969, at 35. The connection between his result and Berry's was made in 1986 by his brother, S. Ramaseshan, working with Rajaram Nityananda. The effect is now generally called the Pancharatnam-Berry phase, and that is not a courtesy.
Where else did it turn up before anybody put a general name on it?
Molecules. Longuet-Higgins and his collaborators noticed it in the late 50s, and Hertzberg and Longuet-Higgins stated it cleanly in 1963. Carry the electronic wave function of a molecule round a loop in the space of nuclear positions, encircling a point where 2 electronic states become degenerate, and it comes back with the opposite sign, a phase of pi. our equator, in a different arena. In 1979, Mead and Trular showed the degeneracy behaves like a solenoid threading flux, and Mead named it the molecular Aharonov-Bohm effect the year after, 5 years before Berry, and confined inside theoretical chemistry.
Why did it take a general statement to make any of that matter? Each of those results is correct on its own.
Each is correct, and each looked like a property of its own subject. Polarization optics has a sphere built into it, so of course solid angles turn up. Molecules have conical intersections, so of course something happens when you go round one. What Berry supplied had no system in it. Any quantum system, any Hamiltonian with parameters, any slow closed loop, and here is the phase, in terms of the eigenstates on a surface spanning the loop. A result with no system in it is one people can go looking for.
And once it was written that way, how long did it take somebody to go and measure it?
Within 3 years, in 2 places that could hardly be further apart. Tomita and Chow, 1986, wound an optical fiber into a helix round a cylinder and sent light through it. The propagation direction traces a closed loop on a sphere, and the polarization comes out rotated by the enclosed solid angle, set by the pitch of the helix, not by the length of fiber or the wavelength. Bitter and Dubbers, 1987, sent polarized neutrons through a helical magnetic field, walking each spin round a cone, and measured the phase against Berry's prediction.
One of those is a classical wave in a glass thread, and the other is a fermion with spin 1/2 in a beamline, and the same formula covers them both. Which is Pancharatnam's point, arriving 30 years late?
30 years late and by a different road. And it settles what the word geometric is doing. Not quantum, not wave, not spin. The shape of a path through the space of available states, and nothing else.
None of this is in a solid yet. It is one spin in a laboratory with a person turning a magnet, and this is a course about 10 to the 23 electrons.
The move is smaller than it looks. In a crystal, an electron state is labelled by crystal momentum, the whole content of Bloch's theorem. Pick a band. For each value of the crystal momentum, there is a state, and as the crystal momentum changes, that state changes. A family of states labelled by a parameter is all the machinery ever needed. The parameter space is momentum space, and the eigenstates are the Bloch states of the band.
What plays the part of my hand on the magnet? Something has to move the electron through that parameter space.
An electric field. Switch one on and the crystal momentum increases steadily. Force equals the rate of change of crystal momentum. The one piece of SCM Psi-BB rim electron is dragged through momentum space by the applied field, exactly as the spin was dragged across the sphere of directions by my hand. And if there is Berry curvature in momentum space, being dragged has a consequence.
What consequence? A phase is not a trajectory. I can see how a phase shows up in an interferometer. I cannot see how it moves an electron.
Because an electron in a crystal is not a point in momentum space, it is a packet spread over a little of it, and where that packet sits in real space is set by how the phase varies across the spread. Drag the packet through the zone and the phase relation across it changes, which moves it. I am not doing that calculation. What it gives is a second term in the velocity, the rate of change of the crystal momentum, crossed into the Berry curvature at the electron's own momentum. A cross product. The extra velocity is at right angles to the push.
That is still a term in an equation. What do the contacts and the voltmeter actually see?
A current flowing at right angles to the applied voltage, with no magnet in the room. A Hall effect without a magnetic field. Edwin Hall found it in iron in the 1880s, within a couple of years of finding the ordinary one, and in a ferromagnet it is much the larger effect and does not scale with the applied field. It was an open scandal for 70 years. Karplus and Luttinger 1954, in Hall effect in ferromagnetics, got an extra velocity term out of the band structure and the spin-orbit coupling.
1954. 30 years before anybody had a name for what they were holding, and in a paper about ferromagnets rather than about geometry. Did the field accept it?
30 years, and for most of them, the term was contested. It looked like an artifact of how they had organized the calculation, and there were rival mechanisms. Electrons scattering asymmetrically off impurities also produces a transverse current, and disentangling the two took decades. Chang and New, in the mid-90s, rewrote the Centley equations of motion for a block electron with the geometry built in from the start, and Karplus and Luttinger's anomalous velocity is sitting there in plain view as the Berry curvature term.
So the picture to keep is that the curvature behaves like a magnetic field, living in momentum space. It deflects, it does no work, it acts at right angles to the motion, and it is not a field that anything in the laboratory produces.
That is the picture, and notice how it is turned round. A real magnetic field lives in real space and bends the momentum of a moving particle. Berry curvature lives in momentum space and bends the position. Arenas exchanged, and not by accident. Position and momentum are conjugate, and the serializer equations treat them almost symmetrically once the geometry is in. Now, none of this happens without magnetism, because time reversal symmetry forces the Berry curvature to vanish, which is why the effect belongs to ferromagnets.
What is it about the magnetization that lets the curvature exist at all? I want the mechanism, not the label.
The magnetization breaks time reversal, so no. Take that back. The sentence before was wrong and I said it too fast. Time reversal does not force the curvature to vanish. What it forces is that the curvature at minus the crystal momentum is the negative of the curvature at plus it. That kills the total when you add over the whole zone, which is why an unmagnetized crystal has no anomalous Hall effect. It does not kill the curvature point by point. For that you need inversion symmetry as well, and the two together do force it to zero everywhere.
So take a crystal that is not magnetic, but has no center of inversion. What is going on inside it?
It has curvature everywhere, equal and opposite at opposite momenta, and you can see it if you populate one region of the zone and not its mirror. Monolayer molybdenum disulfide is the clean case. Two inequivalent valleys, curvature of opposite sign in each, responding to opposite circular polarizations of light. Fill one valley preferentially and the anomalous velocity stops cancelling. Mack, McGill, Park and McEwen measured that transverse voltage in 2014 and called it the Valley Hall effect. No magnetism, no applied field, a Hall signal.
So the sentence I should keep is not that a non-magnetic crystal has no curvature, but that its curvature is arranged so as to cancel in the total.
That is the sentence. And the difference between those two is going to matter enormously 2 conversations from now, when we come to materials where the cancellation is the whole point.
Is there a material where the curvature is concentrated somewhere I could put a finger on, rather than smeared across the whole zone? Because so far it is a function I am told exists and cannot picture.
Graphene. 2 bands touching at a point in the zone, meeting as a pair of cones tip to tip. Berry and Wilkinson's diabolical point, in momentum space, in a real material. The curvature is concentrated at those touching points, and a loop encircling one picks up a phase of pi. That was measured in 2005. The quantum Hall plateaus in graphene sit at shifted positions compared with an ordinary 2-dimensional metal, and the shift is that phase of pi. How a phase moves a plateau is next time's business. 2 groups reported it in the same issue of Nature.
You have twice now said, add the curvature over the whole zone. And I want to be careful because you are talking about the zone as though it were a closed thing.
It is a closed thing, and this is where the hour stops being about phases and starts being about topology. Crystal momentum is not an ordinary momentum. Two values of crystal momentum that differ by a reciprocal lattice vector do not label two similar states. They label the same state. That is a consequence of lattice periodicity, and it is exact, not approximate.
Why the same state rather than two states that happen to look alike?
Because the label enters only through a phase evaluated at lattice sites, and shifting it by a reciprocal lattice vector turns that phase through a whole number of turns at every site at once. There is no measurement anywhere that separates them.
So the Brillouin zone is not a box with walls. The walls are identifications. I have been treating the zone boundary as an edge for years, and it is a seam.
The walls are gluings. In one dimension, the zone is a segment whose two ends are the same point, which is a circle. In two dimensions, it is a rectangle with left edge glued to right and top glued to bottom. Roll a sheet of paper and glue left to right to make a tube, then bend the tube round and glue its ends together. You have a donut. The Brillouin zone of a two-dimensional crystal is a torus.
I have been drawing that zone as a hexagon on a page for years, and never once noticed that the page has no edges.
Nobody notices. The picture is a fundamental domain, one tile of an infinite repeating pattern, and the surface it stands for has no boundary at all. Nothing falls off the edge of the zone. Walk out through one face and you re-enter through the opposite face in precisely the state you left with.
What does having no edges actually buy me? A donut is a nice image, but I want to know what I can now compute that I could not compute before.
Two things, and they are the last two ideas of the hour. In one dimension, it buys you a closed loop for nothing. I had to build my loop by hand with a magnet. Here the zone is already a circle, so sweeping the crystal momentum from one edge of the zone to the other is a closed loop, because those two edges are the same point. That loop has a Berry phase. Joshua Zach wrote it down in 1989, and it is called the Zach phase.
And that phase can take any value it likes?
In general, yes. But if the crystal has inversion symmetry, it is forced to be either 0 or pi, because inversion maps the loop onto itself run backwards, so the phase has to equal minus itself, and only 0 and pi do that. Nothing in between, and no continuous route from one to the other while the symmetry holds and the gap stays open. Two values, not a quantity, a label. The first time in this course that a property of a band has come out as one of a discrete set.
Is that a property of the band and nothing else? Because the loop depends on where I chose to put the origin of my unit cell, and the crystal cannot possibly care about that.
The crystal does not care, and you have got to the caveat before I did. The Zach phase depends on where you put the origin inside the unit cell. Move the origin and the phase moves. What is meaningful is the difference between two situations under one convention. The same lattice dimerized one way against the other, which is how it is measured. Atala, Adelsberger and colleagues, in Emanuel Bloch's group, in 2013, put cold atoms in a one-dimensional optical lattice they could dimerize either way, swept them across the zone with Bloch oscillations, read the phase out by Ramsey interferometry, and got a difference of 97 hundredths of pi, uncertain in the last couple. The prediction is pi.
Does the Zach phase mean anything physically, or is it purely a label?
It is the electric polarization. King, Smith and Vanderbilt showed in 1993 that the polarization of an insulating crystal, a quantity people had trouble defining at all because the dipole moment of an infinite periodic charge distribution depends on where you cut it, is a Berry phase of the filled bands, which explains what had always looked like a defect. Polarization is only ever defined modulo a quantum. The ambiguity in the polarization is the ambiguity in the origin, and they are the same ambiguity.
A defect in the definition turning out to be the signature of a Berry phase. Give me the second thing that having no edges buys me then, because I think it is the one the course has been walking towards.
In 2 dimensions, add the Berry curvature over the entire zone. That is a total flux out of a surface with no boundary, and your own argument about the 2 sides of a loop applies unchanged. Draw a closed loop on the torus small enough to shrink away to a point. A big one going right round the tube does not cut the donut into anything, as you find if you slice a bicycle inner tube the long way. A small one cuts it in 2, the disc inside and all the rest. The loop's phase is the curvature on the disc. It is equally the curvature on everything else with a sign flip, and the 2 must agree modulo 2 pi because the loop cannot know which side you called inside. So the total curvature over the whole zone is an exact multiple of 2 pi.
An integer. Out of nothing except the fact that the zone has no edges, and my inability to say which side of a curve is the inside. No material has entered that argument anywhere.
Out of that, and out of the requirement that the wave function be single-valued. It is Dirac's argument for the quantization of magnetic charge transplanted into momentum space. And an integer has a property that nothing else in this course has had. It cannot change a little. Deform the crystal, dirty it, warm it, squeeze it. As long as the band stays separated from its neighbors by a gap everywhere in the zone, the integer is what it was.
And the only way to change it is to close the gap somewhere in the zone.
You have to close the gap somewhere, which means make a degeneracy, which is where all the curvature came from at the start. The argument closes on itself. Geometry is generated by degeneracies, and only a degeneracy can undo what the geometry did.
Everything in the last hour has worked, and I do not trust anything that only works. Where does it fail?
The adiabatic theorem needs a gap, and every sentence today has stood on it. Move the field fast compared with the gap over h bar, and the spin does get thrown into the other state, and the clean separation into a clock part and a geometric part stops being clean. There is a generalization for fast cyclic evolution, Aharonov and Anandan, 1987, but it describes a different object. A phase fixed entirely by a path through parameter space is a property of the slow limit, not a universal truth.
What else have you been assuming without flagging it? Because a gap I can watch for. A silent assumption I cannot.
That the state I am following is alone at its energy. If 2 states stay degenerate all the way round the loop, the phase is not a number, it is a matrix. Going round mixes them into each other, and loop A, then loop B, is not the same as B, then A. Wilczek and Z, 1984, the same year as Berry. It is used in proposals for computing with holonomies, and it is far less tamed than the case we spent the hour on.
Is there a piece of this that is genuinely open, as opposed to merely harder than what we did? Everything you have named so far has an answer, even if it is an ugly one.
The curvature is only half of a larger object. Provost and Vallée, in 1980, defined a tensor measuring how far apart 2 nearby quantum states are, a genuine distance on the space of states. Its imaginary part is the Berry curvature, which is what today was about. Its real part is a metric, and 10 years ago almost nobody used it. It is now one of the busiest corners of the subject. Superconductivity in very flat bands, optical response, bands too narrow for the usual intuitions, and it is not settled.
And the flat statements of what this simply cannot do, so that I do not oversell it to somebody.
You cannot measure the connection, only closed loops of it. The phase does no work, no energy, no shifted level, no force on anything. And you cannot get an integer out of an open patch of parameter space. You need a closed one. My sphere of field directions was closed because I chose to make it so. The Brillouin zone is closed whether anybody chooses it or not, and that is the difference between a nice piece of mathematics and a property of a material.
The spear and the spin turn out to be one walk, and I can do the spin out loud now. 1 spin, 1 Tesla, field pointing north, split the beam. On one arm, the field never moves. On the other, I walk the field direction round the equator of the sphere of directions and set it back pointing north. The spin comes home pointing north at the same energy, after the same elapsed time as the other arm. And the fringes are inverted, because the loop fenced off 2 pi of solid angle, and a spin 1/2 takes half of it, which is pi, which is -1.
And when you do the whole thing more slowly,
Nothing moves, which is the reverse of what I said an hour ago when I had the leftover down as a leak that goes away if you are patient enough. The clock part, energy multiplied by elapsed time divided by h bar, grows, and it grows identically on both arms, so it never appeared in the fringes in the first place. The other part is a sum over the directions the field passed through, not over the moments at which it passed through them. There is no duration anywhere inside it for slowness to stretch. That is the difference between geometry and dynamics, and it is the same reason the sphere did not care how long the walk took.
you have left the crystal out.
Push it with an electric field, and it does not go where the slope of the band says. There is a second velocity, at right angles to the push, given by the rate of change of the crystal momentum crossed into the Berry curvature at the electron's own momentum. So a field along one direction makes a current across it, with no magnet in the building. In a ferromagnet, that is the anomalous Hall effect, measured for 70 years before anybody could say what it was. And an unmagnetized crystal does not lack curvature. Its curvature is arranged to cancel between opposite momenta. Break the inversion symmetry and the cancelling stops.
And you have not mentioned the donut.
The zone has no edges. 2 crystal momenta differing by a reciprocal lattice vector are one state, not 2, so the faces of the zone are glued to their opposites. And in 2 dimensions, that makes a torus, which matters because a closed surface has no outside. Adding the curvature over it is a flux out of something with no boundary, and the demand that the answer not depend on which side of a loop I call the inside forces that total to be an exact multiple of 2 pi. So a filled band in 2 dimensions carries an integer, and an integer cannot drift.
One thing to set beside all 3, and then the question that is owed. Everything today is generated by degeneracies, not ones the system sits on, ones that exist somewhere in the family. Take every touching point out of the family, and there is no curvature. No curvature, no phase. No phase, no integer. Every geometric statement we have made is the long-range influence of a point the system never visits. The monopole at zero field, the conical intersection in the molecule, the tips of the cones in graphene. And the only way to change the integer is to let the system go and visit one.
So far, the integer is a theorem about a donut, and nobody has shown me one sitting in an experiment.
1980, in the high-field magnet laboratory in Grenoble, in the small hours of the morning. Klaus von Klitzing is measuring the Hall voltage across a silicon transistor at low temperature in a strong field, and the ratio of Hall voltage to current does not vary smoothly as he sweeps. It sits on flat plateaus, and on each, the ratio is Planck's constant over the electron charge squared, divided by a whole number. Reproducible within a few years to parts in a billion, in a dirty semiconductor at finite temperature.
Nothing we have built in 8 conversations permits that. A quantity that precise out of a sample that filthy should not exist.
Nothing permits it, and von Klitzing had no idea he was measuring a piece of geometry. 2 years later, Thulis, Komoto, Nightingale, and Den Nyes showed that the whole number on the plateau is the total Berry curvature of the filled bands over the Brillouin zone, divided by 2 pi. The number we built this hour from a spin and a sphere. Next time, why nature evaluates it so much more accurately than anyone can measure anything else.
So the sphere, the spin, and the donut all get settled at once, on a voltmeter, in a dirty piece of silicon. I want to see that.